All right, so ignoring all of this, we have this as our problem, right? Our nut and bolt here, steel plate, cast iron plate. The thickness of our washer here is 0.095, the thickness of the steel plate is 0.5, and the thickness of the cast iron is 0.75. The diameter of our bolt, which is given in the problem, is 1/2 inches. So we can take this, which is given to us, is all information from the problem, and we can go and construct our full frusta diagram, right? So first things first, what am I going to do? Here in this purple, this is where the washer is. This represents the washer. The blue is our steel plate, and the red is our cast iron. So what do we do first? First, we have to find the midpoint. Where is the midpoint in our system? In order to do that, we add up all of our thicknesses. We get 1.345. Divided by 2 gives us 0.6725. Sorry, my handwriting's bad, and again, this drawing is not to scale. So here's our midpoint line, right? So that means that the widest part of our frusta is going to be centered about this line. See how it goes corner to corner? And so what that means is that where the frusta exits, air quotes, exits our system, those values are going to be the same. And so what I mean by that is, like, here you can see I have these dotted lines. Up here, there's another set of dotted lines like that. And where this crosses here and where this crosses down here are going to be the same value. In order to find those are our DW values. In order to find those, we use this equation where DW is equal to 1.5 D, where D is the diameter of our bolt. Our bolt is 1/2 inch thick, so 1.5 times 0.5 gives us 0.75. So we know that our DW at the top and bottom is 0.75. Okay, great. So now what do we do? Well, we know where our midpoint is. We know the thicknesses of this. The only other thing that's left to do, or we know our DW values, the only thing that's left to do is to find our DW values at critical spots. I don't know if he teaches us critical spots, but that's what I'm going to refer to them as. Our critical spots would be like where the materials like change. Excuse me. So we would have one here at the beginning, one here where it goes from steel to cast iron, and then one again at the middle. There's none down here because it's just all cast iron. So we're going to be looking for 3 points, or three widths. So here we already have our 0.75 because we know that. So in order to find the width here on this line, where you can see I boxed it out kind of, I'll draw it like this. In order to find this width, we use the equation dW plus 2 times, I'm going to use x to represent our depth, tangent of 30. Okay? And so what that'll do is it'll give us our width at any of these points. So obviously if we plug in 0 to this, we're going to get 0.75. So what we do here to figure out our depth, like there, we add our depth. So 0 is at the top, 0.095 plus 0.5 is 0.595, right? Plug in 0.595 into this, and I have a calculator somewhere, and it should give you 2 times 0.595, tangent of 30, plus 0.75 equals 1.437. Do that again, because so now we know what this width is. It's 1.437. And then we do that again here at our midpoint. Our midpoint we know is half the distance of, or half of our total height, I guess, which is 0.6725. Plug that into this equation here, and we'll get 1.527. So now we have our D values, and our D values are this, our big D values are this. Our little d values are the diameter of the bolt, which is 0.5. We're going to use all this to plug into K later. Now I believe, I don't know the equation off the top of my head, but I believe the only other thing that we need is T, and then possibly like the elastic whatever material property. I don't know. But now we need to figure out what our T values are, right? For each of the frusta, or each of the sections of the frusta. So to answer your question, which is why I'm making this video, you asked about the thickness, right? So because the washer is made of steel and this plate here is made of steel, we can treat them as one whole body, or one uniform body. So what that means is instead of having a steel here and a steel here, this whole area here becomes our first frusta. And so the thickness of our first frusta is 0.5 plus 0.095, which gives us, I don't know if you can see this over here, but I wrote already here, 0.595 is the thickness of this frusta here, okay? Now, in order to figure out the thickness of our middle frusta, this area here, how do we do that? Well, we know that this midpoint line has a depth of 0.6725 minus the thickness of our first frusta, which is 0.595, and that should give us I don't know where to write this, 0.0775. So this thickness here of this middle part, I'll slash it out here, I'll just color this in, whatever, and we'll do crisscross x's, whatever. So the thickness of this section is 0.0775. So we use that in our K2 equation. We use the 0.595 here in our K1 equation, the 0.0775 in our K2, and then last but not least, we do the thickness of the bottom section. Now this part's pretty easy, again, because we've figured it out all the way up until this midpoint. So this last section is going to be half of our total height, or the 0.6725 that we calculated earlier. And I believe that is correct. Yep. So once we got that, we know our T values. So we know our thickness values. We know our D values at different points. Sorry, this is a mess. I'm trying to make it as explanatory or the best explanation that I can possibly give. But there you go. I think that's all. Then the only thing that we do from here is take all of our values and plug them into our K equations. Now remember, when we do that, the D value, the big D value that we use, is always going to be the smallest D for our frusta. So here on the first one, which one are we going to use? Our options are 0.75 or 1.4, whatever. Obviously, we're going to use the 0.75. For this middle one, it's 1.4 versus 1.5, so we're going to use the 1.4. And again, on the bottom, we have 1.5 or 0.75, and we use the smallest one. I hope that answers the questions. If there's anything else, just ask in the chat, and I'll